Welcome to Voice Bootcamp, a global name in unified communication. Hello, my name is Faisal Khan, CEO and founder of voicebootcamp.com. In this chapter of CCNP Collaboration Self-Study Kit, we're going to focus on the overview of voice perspective. Now, if you're beginning your journey in Cisco collaboration and you are preparing for CCNA collaboration or CCNP, having an understanding about the overview is very important. So this chapter focuses on the traditional telephone system versus the new generation telephone system. So we're going to focus on analog connection, PSTN, and emerging of voice over IP network. Now, a traditional telephone system, which we are all used to of using it for the last 20, 30, 40, 50, even 60 years, was built around early 1900. It is currently the world's largest and most sophisticated network of devices that are connected throughout the world. Now, unified voice, which is based on voice over IP. A voice over IP network must integrate with the traditional telephony system because you need to communicate between your IP telephony world, which is a new generation, with let's say a cell phone or someone with the old telephone system. So you need to have some sort of integrations between them. Of course, the ultimate feature is the VoIP. However, traditional phone network is not going anywhere anytime soon. Now, the analog connection, which we have been used to since ages, was a phonograph that was a device invented in 1877 for a mechanical recording and reproduction of sound. In later form, it is also called a gramophone. An analog signal which uses a proprietary of a device that captured the audio signal to convey the audio information. So when we actually say the word hello, that is actually an analog signal that been captured into a form so that other person can listen. An analog line which uses a proprietary of electricity to convey those changes. So whatever the information that we are actually saying, or the word, will carry it over this particular analog line using an electricity or some sort of pulse. A signaling could include messages such as dial tone when you pick up the handset, the number that you dialed, and a busy signal if the other end is busy. Now, each analog circuit that we get from our service provider, so for example, when you get a telephone line and connect that to your handset, in that cable there is a pair of wire, not two pair of wire, sorry. With one wire is considered typical ground or tip, and the other wire is called battery or ring. So usually, when the phone is kind of sitting in idle mode, there in between the phone there will be a little breaker right there, circuit breaker. So what happens is it keeps the circuit open. The service provider often sends negative 148 volt toward this particular phone, and because of the circuit being open, it does not get to cross that particular breaker and then go into, let's say, back to the service provider or central office. Now, because of the circuit being open, the phone is considered to be on hook. Now, as soon as you pick up the handset, that circuit will then close. That's called going off hook. And when you go off hook, what happens is this current that is coming in from the service provider, which powers the phone, ultimately gets crossed back to the service provider. At that moment, the service provider realizes the status of the phone has changed, the state of the phone has changed. So when it detects that the state of the phone has changed, what the central office or the service provider will do, provide a dial tone to the phone, and then phone will hear the dial tone. That's when you hear the ring, the ding message or something. You enter the number that you wish to dial. So usually in an analog environment, what you have is when a circuit gets closed in a loop, it creates a state change. So state of the phone has changed from on hook to off hook. When the central office or service provider detects that change, it will then send a signal to the phone by sending a dial tone. The phone will then dial the number, or the user will then dial the number, phone will then transmit that number across the wire back to the service provider. And that information is carried over address signaling. So the first signaling that you have in analog is called supervisor signaling, which is to change the status of the state of the phone from on hook to off hook. Second set of signaling it carries is called the address signaling, which carries the phone number that user intend to dial. Once the phone number is sent to the service provider, service provider will then initiate a connection and give you a progress report. And that is part of your progress signaling. So the progress report could be whether you hear a ring back, the phone is ringing on the other side, or if the phone is busy, you hear a fast busy, and so and so. So kind of an indication as to what is going on with your call. So that is the behavior of a phone. Now, when we talk, our voice, which is kind of an analog format. So as you can see this little graph right here. So the speech amplitude will depend on your loudness of your voice. The louder you speak, the higher the amplitude is going to be, and lower, the more softer you speak, the graphs will indicate according to that. So the analog waveform shown here is a web sign in a form from a human saying hello. Now, the analog signal, there are two types of signals involved in a home environment, in an analog environment. A loop start and a ground start. Loop start is a signal that is typically used for a home environment. Signal is, however, is problematic in a glare environment. A glare is a concept that occurs when you pick up the phone to make an outbound call. At the same time, a call comes in on the phone line before the phone has a chance to ring. At home, this is not a problem because the number of calls that comes into the phone is quite low compared to business. But for business, it could be quite high because business, you could have hundreds of calls coming in at the same time, hundreds of calls being made out by the employee. So a glare is a concept when both sides there is a call coming in and it's trying to seize the same line. So sometime if you are coming from a very old generation telephone system or from certain countries, you might face this a problem when you pick up the handset. Before you even get to dial a number, you already see somebody's talking to you. Or that person could be the person that you intend to dial, could be someone else that are having a conversation, but you're able to hear that. So it basically sees the line both sides, and you just basically see somebody on the other side of the line. Now again, this is not a problem when you have a home environment, but this is a problem when you have a business environment because of the high volume of call. So that's why they introduce a ground start. The ground start signal, which is used in modern PBX design for large and corporate environment. What the ground start does, before the phone can establish a call, the ground start signal will indicate to the PBX that there's a call going to happen. So therefore, the PBX will make sure that there is no incoming call on that particular line. So this is how the ground start will avoid the creation facing the glare problem. The digital connection. The analog signals was almost universally used and very functional even today, where the form, when you speak, you see the signal in a kind of a sine graph or a more analog format. A digital signal, on the other hand, is a binary code that represents the level of voice instead of combination of electrical signals. Now, we remember human voice is still based on analog, so when you say the word on your handset, it says analog. But the digital phone, what it does, it converts that into kind of a different values, or digitizing voice. They are speaking of the process of changing the analog signals into series of numbers. A traditional digital voice uses a technology known as time division multiplexing, or TDM, which basically the most commonly term that you will hear in PSTN world, or public switch telephony network. The TDM ensures that the analog signals, which is in an electrical signal format, gets converted to series of numbers. Digitally encoding multiple conversations at the same time over a single 4-wire path, which generate a binary data to be loaded into the packet. Now, due to multiple conversions that have been digitized, the numeric value are transmitted in a specific time slot known as time division. Corporations use digital voice connection to PSTN, typically implementing T1 circuit in the United States and E1 circuit in the rest of the world. So T1 will be used in the US, Canada, and Japan. E1 or E1 circuit is mostly used in Europe and the rest of the world. Now, as I was saying, a T1 circuit is a 24 separate 64 kilobits per second channel, each of which is called a DS0 or digital signal 0. Each one of these channels is able to support a single voice call. E1 circuit, which allows you to use up to 30 DS0 or digital signal 0 plus 2D channel for voice. Now, whenever you use T1 and E1, you have a choice of using two signaling in digital connection: channel associated signal and common channel signaling. We'll talk more details about them later in the course. Channel associated signal, which is information is transmitted in the same channel as the voice, known as in-band signaling. Where common channel signaling, or CCS, signaling information is transmitted using a separate dedicated signaling channel. Now, the channel associated signaling, which is often known as a raw bit, what happens is each one of your DS0 or time slot, like remember the T1 has 24 time slot, each 20 time slot is actually an 8-bit in binary code, and it takes the last bit, it borrows the last bit from each channel to provide signaling. So because you are borrowing the 8-bit on every 6th sample, what happens is the signaling is embedded into each time slot. So therefore, in T1 that use the channel associated signaling, they get to use all 24 channels for their voice call. However, there are some drawback to that. With the CAS, channel associated signaling, because you are reducing the number of bits available to each channel by 1, what happens, you have less value to play with in order to provide more services. So CAS does not provide all the services that today's world is used to, such as voice, audio, text, everything in the same time. By simply borrowing the last bit, you are embedding the signaling information within each channel, and because the signaling part is part of the same as your voice path, we call this type of signaling in-band signaling. Now, on the other hand, common channel signaling, CCS, which dedicate one of the DS0 channel from T1 or E1 link for signaling information, often known as out-of-band signal, because a dedicated channel will be used, usually the last channel on T1 will be used in order to provide signaling purposes. So you get really one dedicated channel monitoring all the other 23 channel for voice call. Now, because you're dedicating a channel, what happens is that you lose one channel from your voice call. So T1 that use common channel signaling often allows 23 simultaneous voice call because one channel will be dedicated for signaling purposes. It is the most popular because it is based on an existing technology known as ISDN, Integrated Switch Data Network. ISDN Q.931 is a standard that defines the signaling protocol which will be used in that dedicated channel. Most popular because of all the bandwidth is used within the voice channel. So all the 23 voice port that you have, and each port has 8 bits, and you're not borrowing any bits, so all the 8 bits are available for that particular voice call. Now just to show you an example about the difference between 8-bit and whatnot. So if you do a 2 to the power of 8, okay, then you're basically getting a value of 256. Now if I borrow 1 bit and I have 2 to the power of 7, because you borrow 1, your value is 128. So you drastically reduce the value from almost by 50% by borrowing 1 bit. And because of that, you have less information to provide, or bandwidth. Understanding the PSTN. What is PSTN? PSTN is known as the Public Switch Telephone Network. The network that we have, the telephone system that we have in our home, or at least we had in our home. Now PSTN consists of various component or devices that works together to establish an end-to-end call. For example, analog line, it supports local loop, central CO, trunk line, private switch, and digital telephone. Now typically when you have a cable that comes from your service provider such as Bell Canada or Verizon, Etisalat or BSNL, Vodacom, doesn't matter. When they bring a cable to your home, that cable from the service provider's closest switch is known as a local loop. Now typically the further you are away from the loop, the more costly that cellular service is going to be. Now typically home is not a problem because when in a North American residential devices, every area or house or kind of in a group wise, community wise, service provider often has put what they call is a telephone switch, a black box. So from there a cable goes to your home. So that is a local loop. However, because the service provider has to support the entire city, maybe the state or province or the country as a whole, one particular switch cannot serve the entire world, entire country. So they have like that. Likewise, they have many different central office switches, telephone switches. They are located throughout the country. And each one of those switches are connected via a link called trunk line. So between the local loop and a trunk line, a local loop can only handle one simultaneous calls at a time. Trunk line, on the other hand, can handle multiple high volume calls at a time. So it could be like 500 calls, 1,000 calls, 6,000 calls, 10,000 calls at a time. It all depends on the type of interface that you're using. Now, if you have a corporate office, like an office environment where you have an internal phone among the employee who often dials each other via 4-digit, they will have something known as private switch. Similar to this switch right here, except it belongs to that company only. And this private switch also have a trunk line that lets you connect to the central office switch or the service provider using the trunk as well. However, the difference is that the telephone that you have right here in your home will get assigned an extension or phone number from the central office. Whereas the telephone that you have in your office, which is often known as digital phone, gets their extension from this private exchange, a switch. So every company can maintain their own extension range assigned to their employee and decide how they communicate within themselves or external devices. So when you have a PBX, the phone that you get to use in your office will be limited to the support of that PBX that you're using. So the phone that you use will have to make sure that it supports that PBX. Not all phones supports all PBX. Now, PBX or often key system are internally to manage an in-house phone such as an office environment, allowing internal users to make phone calls inside the office without using any PSTN resource. Calls to PSTN will be forwarded out to the company's PSTN trunk line. Now, when you first look at the PBX, it looks like a large box full of cards. And those cards could be line card, trunk card, and a control card. Now, the line card is basically, think about like a patch panel. Every phone that you have will come in from every desk. The phone will connect to the line card. So if you have 25 phones, you should have a line card with the 25 ports. Now, the trunk card connects to the service provider via E1, T1, or maybe a few other options that you might have. Control card could be the internal communication between these devices. So that's like a kind of motherboard environment where all these line card and trunk line, they communicate with each other. Now, connection to and within the PSTN. The home users and office, small office can connect using analog ports such as FXS and FXO. Each two-wire in analog connection has the capability to support a single call. For a small and a large business with a multiple incoming calls coming in at a time may need more than a single telephone line. They usually use T1 or E1, which may consist of 23 to 30 voice calls respectively. As the business grows, you can consolidate the multiple analog connection into one or more digital and E1 connection. So here's my PSTN. So you have an analog line coming into your home, such as FXO and FXS. FXO stands for Foreign Exchange Office. FXS stands for Foreign Exchange Station. You have a digital connection such as T1, E1. You have a multiple analog connection in FXO and FXS. And then you have a multiple digital connections also allowed as well. Now, one of the most important thing in a telephone network is the numbering plan, PSTN, similar to assigning an IP address to a computer. Company will manage their own internal numbering system using 4-digit or 5-digit extensions. If you go to any company these days, you often see that employee has 4-digit extension on their business card, or they have a 5-digit extension. They call each other internally as if they're just dialing, by using 4-digit. Now, a valid E.164 number, which is a fully qualified telephone number, must be implemented whenever you are connecting to real world or PSTN. Now, E.164 is a standard name for a telephone number that is managed by International Telecommunication Union, ITU, which I believe they are under the United Nations Charter. Each number in the E.164 numbering plan contains the following: a country code, for example 1 for Canada, national destination code such as a city or area that you're in, 416, and then subscriber number. Now in the subscriber number, you have a portion that represent the company that you're with, 839, for example. That is a telephone number that belongs to Fido, the telephone company that the number belongs to, and my extension could be 1717. So that your actual number could be the last four digits. So when you advertise the phone number 1416-839-1717, you might think that that is your telephone number. In reality, your actual number could be the last 4 digit or last 7 digit. So E.164 number are limited to maximum length of 15 digit. So it can never go beyond that. Now, the country code right here, which is often assigned to a country by ITU. They are the individuals, the organization responsible for assigning country code to each country. Now what goes below that, such as 1, or what happens after that, is managed by the whoever is responsible for the telecommunication in that particular country. So in North America, such as Canada, US, Mexico, we have an organization known as NANP, North American Numbering Plan. I'm not sure if it's really an organization or a consortium of a group of service provider working together. What it does is really basically manage the dial plan between all these 3 countries. So likewise, many other countries have their own organization bodies, either at the government level or the private sector level, doesn't matter, will be responsible for dividing a numbering scheme for their countries. Like they will decide what should be the city code, what should be the province or state code, or whatever that you want to define. So these numbering plans are very important and dictate how you reach an endpoint. Now, as I said, North American Numbering Plan, NANP, is use E.164 standard to break down the numbers into the following component: country code 1, area code 416, city code of Toronto, CO or exchange code 839, FIDO mobile company, station code or subscriber code 1717. So the full number will be 1416-839-1717. When you're calling that number from, let's say, India or Japan or any other country, what you're really doing, the first few digits of the number is actually used for routing purposes. They basically decide to route the call based on what is the first country code. So when they see the first code is 1, so the Japan Telecom will then forward that call to the Canadian provider, or the provider is responsible for routing calls for Canada on behalf of Japan. Then when the call comes into Canada, wherever the call lands, that service provider will look at the remaining digit 416, realize that that call is for Toronto. So that call will be then routed to whichever service provider or switch responsible for managing the Toronto connectivity. The call arrives in Toronto. Toronto main service provider looks at the 839, realize that belongs to FIDO. So it forwards the call to that company, mobile company called FIDO. FIDO will then look at the last 4 digits and realize, well, that is my subscriber. That is one of my customer. So I'm going to send a signal to whatever the frequency that or the port that customer is registered to. So that's basically how the call actually goes through from one end to another end. So that's the overview so far we have talked about was telephone, analog and PSTN. So the next is emergence of voice over IP. Now, there's a 2 different terminology here. Unified voice as voice over IP. So they're 2 different things. Think about voice over IP as a road, a street, a highway. And what it creates that transport path. What carries on that highway will depend on the type of vehicle that you have. For example, if you have a highway that connects one end of the country to another end of the country, but on that highway you have trucks, you have regular car, you have buses, you have motorcycles, whatever the device. Those individual components are known as the unified voice. So unified voice is basically the application that carries over that VoIP path. So the biggest benefit of VoIP to business is saving cables and related to infrastructure cost. It reduces the cost of communication because you don't have to run expensive cables under the ground or satellite connectivity. You already have internet. Most likely they are already connected. So you can simply route the call over that. It reduces the cost of cabling, seamless voice network. Take your phone with you, so because you don't have to worry about any cable physical restriction, you can literally take your phone with you wherever you go. There are many hundreds of thousands of software based phones such as IP Blue, IP Communicator, X-Lite. They're available online for free. Some of them are free of charge, some of them are for purchase. Some of them work openly with pretty much any PBX, while some only works with certain PBXs. Also, you have unified email and voicemail. Now, unified email and voicemail is when your voicemail, such as somebody leaves a voicemail, will come or delivered to you in a form of email. It increases productivity and it provides open and compatible standard network. Now, remember, we human communicate in analog form. So whatever I'm saying today, right now, and you're hearing, is actually an analog form. It's like a sine graph. As long as that sine graph goes up and down, like a heart monitor in a hospital, as long as it goes up and down, you're all good. If it's straight, then you're in trouble. Okay, so our voice analog has to be converted into a digital format. Now, to be able to do that, they had to come up with an algorithm how to take a human analog voice and convert to digital format. By a scientist named Dr. Harry Nyquist, proved that to convert voice to packet, it needs 3 steps. You need sampling, like taking a sample of the conversation, quantization, and encoding. Now, the scientist, Nyquist, found out that he could accurately reconstruct an audio stream by taking a sample of analog voice, such as my voice, twice. So whatever I say, taking it twice of that, as many times per second, as a numerical value of the highest frequency used in the audio. So you basically take the highest amplitude, and you realize that human voice does not go above 4,000 hertz, because in sound is actually measured in hertz and kilohertz. So to take the twice a sample, you would multiply 4,000 into 2. So that gives you 8,000 sample per second. Now you take that 8,000 sample, which is a numeric value that is encoded by a single byte, 8-bit of information. So that gives you 1 second worth of voice. Now, transition between the steps in digital measurement is known as quantization. So the process of converting from analog to digital format is known as the quantization, where these wave signals that you have up and down, it gets converted into zeros and ones. And this is called quantization, the process. Now, encoding binary, as it gets converted from this wave into a binary format, it is assigned a binary value, and that assignment of binary value to that quantization measure is called the encoding. The codec will use the 8 binary bit in each byte as a 2 component, a positive and a negative indication. So when a packet starts with 1, that's considered to be a positive. When it starts with a 0, that represents a negative value. Again, this is just for your information. They don't cover that in the exam. You don't really have to worry about that in a real world scenario either, unless you are like developing some sort of advanced algorithm, arithmetic or something like that. But usually in most implementation, we don't really care about this, to be honest. Anyway, that's good to know as far as your own information. Now, the theory dictates that you need 8,000 of these samples every second in order to create 1 second of voice. So each sample is 8 bits. So therefore, 8,000 multiplied by 8 gives you 64,000 bits. You divide that by 1,000, that gives you 64 kilobits per second. So you may have seen the word 64 kilobit per second very often. Well, that is the baseline, and that is the human, the maximum bandwidth of your voice call when you make a phone call, let's say over a satellite phone, or doesn't matter. It is the uncompressed traffic. And this uncompressed audio traffic is often categorized as a term called G.711. No, it is not the 7-Eleven store. It is G.711. The word G a letter followed by 711 represented by the ITU standard. So anything with ITU standard, they will start with a letter followed by 3-digit number. So ITU standard G.711 dictate that the voice traffic is uncompressed and the maximum payload size should be 64 kilobits per second. Now there are two forms of G.711, mu law and a law. This is not U. This is the Greek term mu law. Mu law, which is primarily used in United States, Japan, and Canada. A law, where is used everywhere else. Basically, what it does, it dictates the sound behavior of the end devices in each country. An example would be when you are in England and you hear the phone ring. You often will see the phone ringing in England is totally different than the phone ringing in Canada or US. In Canada and US, you will ring, 2-second pause, ring, 2-second pause. In a certain part of the world, it will be like ring, 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 like right in a continuous form of ringing. If two devices, one from Canada, one from England, needs to communicate, and because there are two different versions, mu law versus a law, the North American side, mu law, has to convert it to a law format in order for the communication to be successful. And that is the job of the voice switch or telephone switch. Now, we know that G.711 is the uncompressed traffic, 64 kilobits, the best quality traffic you can think of. And the maximum speed of that is 64 kilobits. How did we came up with that formula? We took 4K kilohertz, multiply by 2 because twice the sample, multiply by that 8 bit per sample. So that's a bit right here. Oops, you can see my handwriting is the best. So 8 times 8 gives you 64 kilobits per second. Now that is the uncompressed. Now back in the early days, traffic at that rate was quite expensive because 64 kilobit used to be a leased line back in the 1990s or 94, 91. I remember when I first deployed a leased line in Bangladesh, 64K leased line was like almost $4,000 a month dedicated. Can you imagine how many voice calls can you run on that? Just one. So in order to save bandwidth, even in North America or Canada, US, Europe, doesn't matter, we may have this amazing amazing package that allows unlimited bandwidth for both residential and business. But for most cases, they're not really unlimited. They still meter you. They still control how much bandwidth you can use per month. So to be able to reduce the bandwidth on a lower WAN link, they had to come up with different algorithm to convert so that uncompressed traffic get compressed in order to save bandwidth and then decompress on the other side. This concept of compressing and decompressing is known as the codec, which enables you to compress the number of samples sent and thus use less bandwidth. Significantly reducing the amount of bandwidth comes at a cost because you're going to have a quality issue. Now, the next algorithm that they invented was by reducing the number of bits that they use to send compress the traffic. Remember, 8 bit per second, 8 bit per sample, which is 8,000 samples. 8 times 8 is 64. But what if I take 4 bits instead of 8 bit? So they come up with a more advanced circuit that is able to take only 4 bits instead of 8. By taking that, everything else remains the same. By taking that 8 bit into 4 bit, you are actually reducing the bandwidth by half, 32K. Now that is called G.726 bits per sample using 32K bit. So it's actually G.726 32K. This standard is known as ADPCM. the word ADPCM stands for Adaptive Differential Pulse Code Modulation. Adaptive Differential Pulse Code Modulation is a variation of different pulse code modulation that varies in the size of quantization steps to allow further reduction of required bandwidth for a given signal to noise ratio. Now, this basically the advanced circuit they created in a real world. Now, what if I take it, instead of using 4 bits, they end up taking 3 bits. They realize that they could reduce the bandwidth to 24K. Taking 2 bits gives you 16K. So this category were grouped together into G.726. Okay, they're not still high compared to 6, but they're still way less than 64K. Now, while the technology continued to improve, they did more in research, and they came up with something called LDCAL, Low Delay Code Excited Linear Prediction. It is a voice data compression algorithm that used low coding delay of less than 2 milliseconds. LDCAL is used in the ITU G.728 specification, which gives you 16 kilobits per second. Then you have more advanced algorithm introduced called CSACAL. CSACAL it stands for Code Excited Linear Prediction Speech Coding. So basically, it's a type of audio data compression algorithm for voice that compresses a digital voice in packet of 10 milliseconds duration. Now, because of its low bandwidth requirement, G.729 is mostly widely used codec in a voice over IP world in a WAN site. Now, G.729, which provides you 8 kilobits per second, has various variation. For example, you have G.729, the original codec, use high complexity algorithm. Then you have G. Let me open a notepad. Alright, as I was saying, that you have G.729 codec in original format, use, let's say, high complexity algorithm. Then you have a G.729A or ANX, they call it. So what it is a medium complexity variation of the G.729, and it is compatible with G729 high complexity. However, it uses less complex that has slightly lower voice quality. So less complex and lower voice quality. Right, just to make sure the font size is bigger. Then you have G.729B. Now G.B, or often known as BNX, which is with a silent suppression. Silent suppression meaning that if one party talks, the other party obviously is quiet, listening. So the party that is listening is not going to generate any traffic. So it's basically suppressing the silence. And it is not compatible spell check. It is not compatible with the previous two. So that's one of the things that you have to keep in mind. Now, then you have the last one called G.729AB, or so in this scenario, G.729A with silent suppression and only compatible with G.729B. So basically saying that G.729A compatible with G.729B. So if you have G.729 in one side, if you realize the one of the side has G729B, then you can use on your side either G.729B or AB. So those are some of the variations you have. Anyway, you can always Google more details about them to get more details, knowledge about each particular codec. Now, these codec, when they are designed, you have different, like I say, codec G.711, G.722. Both G711 and G722 are the same type of codec, 64K, except that it takes less processing power to generate G.722. Now, these codec are provided what they call a score. Mean opinion score is basically a score that you provided by a bunch of engineers sitting together listening to voice and say, you know what, this is 5, this is 2, this is 3. Anyway, higher the mean score, the better the quality. Lower the mean score, mean opinion score, obviously lower the quality. So MOS score for G.722 will vary depending on the testing methodology. G.722 is generally accepted as a better than G711 in terms of its speech quality. Cisco Unified Communication, you will hear two codec frequently referenced, G.711 and G.729. Cisco IP phone includes a codec that can encode and decode voice in either one of these two formats. Now, G.711 is a common ground between all VoIP devices. G.722 as a default codec using on new Cisco IP phone and in firmware for existing models that can support it. G.722 is classified as a wideband codec, better quality than G.711. Use the same bandwidth but is slightly more complex codec to process. G.729 comes in two different formats. G.729A, G.729B. A sacrifice some audio quality to achieve much more processor efficient coding process. B introduce support for voice activity detection. Digital signal processor, DSP, is the main component within a Cisco router that is responsible for providing packetized voice to data and vice versa. DSP is a chip that performs all the sampling, encoding, compressions that we just talked about. That is the module that does all the trick. And they are quite expensive. DSP typically come in as a chip to install on a Cisco router. Now you have an embedded one on the motherboard, or you can add it in a Razer card. Cisco provides DSP calculator that allows you to calculate how many DSPs you need depending on how many simultaneous calls you have. So these are the model number of DSPs. For example, PVDM3. PVDM stands for Packetized Voice Data Module. Packetized Voice Data Module. The number 3 represent the third generation, and these values 16, 32, 64, they represent the number of simultaneous calls that can handle. PVDM3-16 can handle 16 simultaneous uncompressed call. PVDM3-256, one chip can handle up to 256 call. Now, DSP, with some codec consume more DSP resource to pass through audio conversation process than other codec. So they are divided into two categories. So all your codecs will be divided into medium complexity versus high complexity. In a medium complexity, it will take less processing power, but it will also give you less number of calls. Sorry, more number of calls. Whereas high complexity will take more processing power, thus gives you less number of calls. Each DSP chips, PVDM3, can handle call more efficiently and can handle more high complexity calls per chip than the older version. Now what the DSP chip does, they provide RTP voice traffic. They convert your audio into a packet. Now the protocol that actually carries the conversation between you and I is called RTP, real-time transport protocol. That is the protocol is used to transport the your voice traffic. Now regardless of what kind of signaling protocol you use, we'll talk about signaling protocol in the next few chapters. Every RTP, it will also have something called RTCP protocol, or real-time transport control protocol. RTP is a protocol that carries the voice. RTCP is monitoring that quality of that voice. For every RTP operate at a transport layer, an RTCP will follow. You can use the RTP for audio and video purposes. RTP engage when two devices attempt to establish an audio session on a UDP port in this particular range. If there is a firewall between them, make sure you open up these ranges. Two-way conversation, the device establishes a dual point-to-point RTP stream, one in each direction. RTCP also engage for statistic reporting such as packet count, delay, packet jitter, and losses. So as it across the network, and if it experiences any of this problem, RTCP protocol will be used to report that back to the device. So administrator can monitor the status of those reports to see if they're facing any network issues. RTCP will use the odd number port following the RTP port. So if RTP use 16384, RTCP will be 16385. So it kind of follows that. So if you look at whatever the port number for RTCP, subtract 1, that will be the port of the RTP session that it is following. Alright, so that's pretty much it for the introduction of what voice over IP is. And so that concludes this particular chapter, and I will see you in the next.